Hi there, it's John Pushkar. I'm here today to bring you another episode to provide safety insights and important tips in the world of fuels and combustion system safety. Today's episode is all about preventive maintenance and troubleshooting. Does your team have the talent to really safely troubleshoot fired equipment? Do you really want to continue to rely forever on outside folks that you call in and be at their beck and call? Do you really want to have to expect that they're going to come in at 2 in the morning or on a weekend or a holiday? Have you noticed how hard it is to get a hold of these people lately, and how few of them there are, and the kind of money they charge? You don't have to continue to live this way. Over the last 40 years, I've developed and led fuels and combustion equipment safety programs for the largest manufacturers in the world. Today, I'm bringing you knowledge, insights, and best practices about fired equipment and natural gas safety. Over the next few minutes, you'll get the kind of practical, real-life explanations that I've become known for. I provide training annually to many organizations in many different industries. I help them create preventive maintenance programs that meet all of the legal requirements. I help them create and implement preventive maintenance, safety, inspection, and testing programs that meet the requirements of codes and standards, and also provide for best practices that they may have never heard of. I help them to create gap analysis systems so that they can understand what the overall state of the safety devices on their equipment is versus today's state-of-the-art systems. You need to understand that human error is the #1 cause of accidents, and training is the #1 way to minimize the risks for human error. So what do I mean by training and helping to provide you with your own capabilities for preventive maintenance and troubleshooting? What I mean is making sure that your people have both the knowledge and the hands-on skills to address issues with your equipment on site. I can't do the impossible. This doesn't happen overnight. I can't provide them with enough information to be dangerous, but I can make them very aware of what the most hazardous of conditions are. I can put them in a position to understand the basics of what's going on, how fuel systems work, how to recognize imminent hazards, how to evaluate flames, and I can provide them with some very basic hands-on testing instruction so they can at least be doing things like testing flame detectors, testing low water cutoffs, testing gas pressure switches, and a number of other components. I can put you on a path to being self-sufficient in the fuels and combustion system safety world. If you operate this kind of equipment, it's a basic responsibility you have to yourself, your people, and the organization. I'm going to share with you a clip from the Prescient Technical Services online school about testing safety devices. Even just this module could open your eyes to a number of things that you should be doing. And at the end of the day, the life that you save, it just might be yours. Welcome everyone to Module 3, Fuel Train Safety Device Testing. Actually, we're going to speak a lot about not only safety device testing, like the pressure switch that you see in the inset of the slide here, but we're also going to discuss all of the other devices, components, valves that are part of a fuel train and other safety devices associated with particular types of equipment like boilers and fired heaters. And we're going to talk about code required things that you need to be doing on at least an annual basis. So again, we'll talk about interlock devices, we'll talk about valve testing, and then we'll wrap up with talking about inspections and evaluations. So we're talking about all of this because these are things that codes and standards require us to do to be in legal compliance. So codes and standards want you to do
things that are specifically identified in their text in the document, but also whatever a component manufacturer requires. So these are things like interlock and trip testing. There are also installation issues. And then kind of a concept that I've coined that I like to do for my clients is I like to create a gap analysis or design compliance verification program. And what this means is I like everyone to be constantly aware of where they don't meet the code of the day. So codes and standards like NFPA 85, combustion hazards for boilers, and 86, standards for ovens and furnaces, they apply and you must comply with them the year that you install something. But most of what they have is not retroactive. So for example, used to be that there was one pilot solenoid required on an oven or a furnace. Now there's 2 required in series. It's a relatively inexpensive fix. So I like to have questions on a checklist that identify that maybe that isn't in place. Everything that's in a standard in a code typically is gotten there because someone's got horribly injured or there's been some devastating catastrophic event at some time. So it's good to know that's kind of a stretch goal, meaning to comply with the latest code and standard. So what I like to do then is identify things that are absolutely required. Then I like to identify things that are not in compliance with the most current standard, this gap that exists. Then folks can take a look at prioritizing the risks and consequences of things that they're not in compliance with and start to create an action plan and whittle away at those other items. Other additional testing and inspection practices we'll talk about are things like the opportunity to apply new technologies to improve reliability, reduce maintenance, reduce risks, best practices that I've become aware of from 40 years in the business that are kind of proprietary, but I'll be disclosing many of these in these modules to come. And then also to identify and recognize hazards that exist as this testing and evaluation is taking place. So there's dozens of things to test and inspect. There are really good lists in the annex of ASME CSD1, which is codes and standards for safety devices for boilers less than 12,500,000 BTUs an hour, and also in the annex to NFPA 86, standard for ovens and furnaces. Now, there's a bunch of things that are kind of basic, but there are specific devices for specific sizes of equipment and types of equipment. And obviously, we're not going to cover every interlock, trip, or safety device for every kind of fire device that's ever been known to mankind. But we'll cover most of the big items that you really kind of need to know about. So when you do interlock and valve seat leakage testing, it's functional testing. It's not simply calibration or set point verification. When I interface with people who do a lot of instrumentation work, I often find people saying, yeah, we have a calibration crew. They've calibrated everything. But we're really talking about functional testing. It's a different thing. The other thing you have to be aware of is that before you embark on a functional testing program, you have to know that obviously you might find things that are wrong. So finding things that are wrong means there might have to be equipment that's taken out of service. You might have to have spare parts readily available. There could be hazardous conditions that are now have revealed themselves, which might have very important longer-term equipment useful life implications. So there's a lot to talk about. There's important scheduling and communication that needs to be done. You don't want to end up, for example, surprising someone with the fact that their key piece of process equipment needs to be down for a week while a part comes in. And that's speaking from experience. And again, we'll also be discussing valve seat leakage testing. So if you've ever wondered, why do we really test these things? Is it because they kind of just naturally fail over time? Yeah, that's part of it, of course, sure. But then there's also things that people do that are just absolutely stupid that we could never predict. Like if you look in this particular case, here's an airflow switch where someone has terminated both conductors on the same lug. So this is obviously a switch that had failed. Instead of actually replacing the switch, somebody took a shortcut here, which certainly puts the safety of this piece of equipment definitely in jeopardy. In case you haven't seen where it is, that's where it is. Then there's this particular case where we've got another pressure switch that's failed and someone stuck a popsicle stick to jam the switch mechanism in place. So again, you just can't predict what kinds of things have occurred over time. This is all part of the reason why there are safety device testing programs. So what are the requirements? Well, there's two tests that need to be conducted for each device. One is just to make sure that the device itself functions. So does the switch make or break at the expected set point? But then there's also, does the proper function occur after you've actuated the switch? So we need to test devices and we need to validate that the proper functions occur as a result of those devices tripping. This is why we really like to test devices in the field as they're hooked up and wired, and not necessarily taking them off of equipment and testing them and then installing them back on the equipment. If something's supposed to shut off safety shutoff valves and stop gas flow, we want to see that that's what actually occurs. So again, I talked about what are some of the questions that need to be asked before you're actually there trying to test something. So things like, hey, do we have spare parts? Where would we get replacement parts, switches, or valves, and when? You should know that, for example, some Maxon safety shutoff valves are 6 to 8 weeks once you order them. Will we be taking equipment out of service immediately if safety defects are found? And of course, the answer should be yes. There really are no workarounds to some of these devices, like a flame proving device. If a optical flame detector has failed, you really don't want to bypass that and not know if it goes out. If a flame goes out and we're still pumping fuel into something, we could have a catastrophic explosion that could kill people. So these are things that need to be explained to operations people or to business people, for example, about what we're going to be doing and why. Then the other things that you need to think about are, how are we going to communicate about safety issues and how will we document them? There have been circumstances where, we've identified things that have failed. Everybody signed off, they agreed that something's failed. Somehow mysteriously things get running and you find it again the next year when you go to test. If there would have been an incident possibly and someone would have, God forbid, gotten hurt or killed, this is a circumstance where it's a willful violation and frankly probably personal criminal liability. So again, think about processes where things are going to get documented and things are likely to get repaired. So other things you need to do besides communicating, thinking about spare parts, are you need to identify correct set points for devices. So set points can never be a setting at completely one end of a switch or the other. If you find that in the field, then you know that the switch is not set right, or it's frankly someone selected the wrong switch. You shouldn't be trying to operate a switch at one end of its range or the other. But things like high and low gas pressure switches, combustion air proving switches, and even purge timing need to have the proper information identified ahead of time so that you can test to see if things trip at those particular set points or not. Likewise, you need to evaluate purge timing, and we'll talk about that. So where do you get these set points? Well, I've gone to places and said, do you have these set points? You know, you need the proper set point information. And when we say this, we don't mean go into the field and write down the set points that are there. We need you to understand that these are proper set points, that they have been commissioned, that they've been evaluated. If you don't have them or you don't have confidence in them, you need to recommission these devices and obtain the proper set points in the field. So it's unlikely that you're going to find these on a drawing or from the device manufacturer, because generally they would need to be derived in the field when this equipment is put into service. So, for example, I say their high gas pressure switch, highest gas pressure that can still operate a burner with a stable flame. So someone needs to be there in the field adjusting the gas pressure with the flue gas analyzer in the stack with an eyeball on the flame to evaluate when the gas pressure is making the flame unstable or putting, for example, a bunch of CO into the flue gases. Low gas pressure. So someone will have set low fire when the thing is commissioned and started up. Someone should be backing down the gas pressure to see at low fire when does the flame start to get unstable. And again, sometimes you can't see this on a flame detector. It has to be someone with experience who knows what an unstable flame looks like, and you might not even see a lot of it in the flue gas constituents. It's someone with a lot of skill and experience to evaluate and set this. And then likewise, combustion air proving. It's almost something where you need to measure, make sure you got the right amount of combustion air for a purge, make sure the purge timing's right, and then from that information and evaluating flames, you would be able to properly determine what the set point for the switch should be. So here's an example of just what I mean by stable flames. In this table, I'm showing you CO, carbon monoxide, basically a combustible, basically a surrogate indicator of having too rich a combustion, generally speaking with standard burners. I'm showing you excess oxygen in the stack, and you can see there's an inverse relationship as you would expect. You can see it goes from 4% down to 0, and as O2 goes down, CO goes up. It makes sense if you'll recall our combustion basics module and balanced chemical equations for combustion. But I'm also showing you here percent excess gas pressure. So if at 100% gas pressure, and what I mean by that is I'm at the design stable flame amount of gas pressure, and in this case it was 5.4 inches water column. I had 4% excess oxygen and 6 parts per million CO. Pretty decent setup, right? I give it 10% more gas. I go to 5.94, 0.54 more, 10% of 5.4. And you can see the O2 goes down a little bit, CO goes up a little bit. Not much. But as you continue to increase, when we get between 30 and 40%, you could see that it starts to be an exponential increase. So you could see, for example, that maybe you'd want the high gas pressure switch set at 7 inches water column, because after 7 inches, it really starts to go bad very quickly.
Hi, it's John Pushkar. I hope you found this episode useful. If you'd like to know about more ways that I can help, you can check out my website at www.prescientts.com. There you'll find information about the Prescient Technical Services online school, my book, Fuels and Combustion System Safety, What You Don't Know Can Kill You, and also about some of the consulting projects that I've been providing to clients for the past 40 years. Things like implementing inspection and testing programs on a corporate enterprise-wide level, things like reviewing and commenting on capital equipment purchases that involve combustion equipment, and even being a legal expert if things go really wrong. Once again, thank you for attending, and remember, be safe out there. The life you save, it just might be yours. Folks, I hate to go here, but I need to provide you with a disclaimer. I never know how people are going to interpret the things that I say and present, so I've got to make it crystal clear here. Most of the things I talk about require very specialized knowledge to implement. The courses that I offer are awareness level courses. There's good information in there, but being able to actually implement these things requires both knowledge and skills. Knowledge is what we learn in books, what you learn watching me, listening to me. Skills are the hands-on part that we can't do together over a video. So please don't take a little bit of this and have enough information to be dangerous. I need to tell you that neither Prescient Technical Services or myself, John Pushgar, the presenter and author of this work, warrant or represent expressly or by implication the correctness or accuracy of the content of the information presented. The user or viewer of this work accepts any legal liability or responsibility whatsoever for the consequences of its use and its misuse. Thank you again for watching this episode, and I look forward to having you back.